it's a great pleasure to introduce Mike Kokkoris from the National Technical University of Athens. Mike was actually here in the US quite a long time ago. He was down at Texas A&M. And then after a stop in Belgium, he went back to Greece and he's been there ever since. Since 2003, he's been faculty at the National Technical University of Athens. So he's visiting MSU this week, and we have the great pleasure of hearing his talk now. And I wanted to say that if anyone here locally would like to arrange a meeting with him, just let me know, and I'm happy to set something up. So without any more delay, please, Mike, go ahead.
Yeah, thanks a lot. It's a great honor and a pleasure for me to be here. I come from the maybe the oldest technical school in Athens, Greece. It was founded in 1830. I have a picture just in front of you of the National Technical University. Actually, it is the most prestigious establishment of higher education in Greece, and currently, as a matter of fact, two of the graduate students at MSU, namely Miss Artemis Sadiri and Mr. Ioannis Trimis, were either undergraduate or graduate students of the National Technical University of Athens. Nevertheless, the most illustrious, maybe member, ex-member of our group, was currently Professor Artemis Spyrou, and I was her first. I had the honor to be her first postdoc, as a matter of fact, at our research facility at Demokritos, and she wrote her first publication with me, for which I'm really grateful. So I'm going to present to you an overview of our recent research activities at the nToF facility at CERN. And these activities are related, of course, to neutron data and basically nuclear astrophysics. But since CERN is basically known for high energy physics experiments, most people don't know that there are two major low energy nuclear facilities at nToF and at Isolde. And they have been operating since 2001, nToF. And so we're celebrating 20 years of its foundation this year. And basically, nToF is a pulsed neutron source with different paths, different beam lines. And it has it can cover a wide energy range for experiments, and has a high intensity, most probably the highest intensity in neutron beam worldwide. And the data that are produced by nToF, by definition, are used in astrophysics to study stellar evolution in supernova, and for studies how to incinerate radioactive nuclear waste. So the neutrons at nToF are produced via the spallation process. We have 20 GeV proton pulses from the proton synchrotron, the old PS at CERN, and they are impinging on a lead target. The pulses have a very narrow time width, but a very slow repetition rate, about 1 pulse per second or even less. We have currently two experimental areas, namely area 1, that's the oldest one, and area 2. Area 1 is along beam line with a slight inclination. The distance is 185 meters away from the spallation target. So it has excellent timing capabilities, but the neutron flux is slightly reduced. And then we created a few years ago area 2, which is in a vertical configuration, about 20 meters from the spallation target. The neutron flux is really high, but of course the time and accordingly the energy resolution is relatively limited. So here we have the basic neutron flux relative to the energy. In area 1 and area 2, you can see the much higher neutron flux at area 2. And there we can measure low mass, high activity targets or low cross-section samples. And in area 1, we have much better and time energy resolution. So area 1 is currently used for fission measurements and gamma reactions, basically related to S process, not so much for R process. And area 2, unfortunately, only for fission measurements for the time being, because our detectors cannot tolerate the high neutron flux. And we have to solve this problem as soon as possible. But this is basically the situation as it is right now. So the pride of area 1 is the total absorption calorimeter, which is a 4 pi barium fluoride sphere for total cross-section measurements of neutron gamma reactions. You can see on your right hand side, you can see these are the barium fluoride crystals, polygonal pentagons or hexagons. They are covered with carbon fiber enriched in boron, and there is a plastic here with lithium-6. All this is to reduce the counting rate from scattered neutrons originating from the target, and basically to limit the analysis on gamma rays, where the efficiency is really approximates 80 to 90% or even 100%. So it can act as a multiplicity filter for neutron capture reactions, and it can yield a high quality, accurate cross-section results. Now, the pride of area 2 is the micromegas detectors for fission studies. These are gas detectors, and on a micromesh configuration, on your left-hand corner, you can see the basic setup of a micromegas detector. It's ultra thin, so it creates very small background for neutrons. This is the sample, actually, the radioactive sample, which forms one electrode. Then this is the drift region where the fission fragments ionize the gas, and we have the high field amplification region where cascades occur and the signal is enhanced. You can see here my ex-PhD student, Thanos Stamatopoulos, who is currently at Los Alamos, and using this elaborate, dress to mount the neptunium and the plutonium targets on a stack of micromegas detectors, which was later put in area 2. And that was actually the first experiment that was carried out in area 2, and it was carried out by our group. So now, and when I'm talking now, I mean really now, during the last 2-3 months, we're trying to set up a new experimental area. This experimental area will be put exactly close to the spallation target, and this will allow us to have an extremely high flux, so we can do both nuclear astrophysics and, as I'm going to show you in the radiation damage studies. For nuclear astrophysics, we need proper moderators, and this needs further experimental study. In this NEA station, as it is called, because it's very near to the spallation target, one with a proper choice of moderator can create a Maxwellian-like neutron spectrum and can measure Maxwellian average cross-sections. So you can see on the left-hand corner, with the use of moderator, how the whole spectrum, according to simulations at least, is changed. And this is a famous resonance in gold. And you can see that the spectrum is really close to a Maxwellian average spectrum, which is been noted by the green line. Ours is currently with the purple line, and this is behind a 1.5 centimeter boron moderator. It's really close. It needs further experimental studies, but this, these are simulations, and you can really trust simulations. It needs further experimental verification. I put here just a very short list of selected recent publications, because there are hundreds of publications coming from nToF related to nuclear astrophysics. And I have a small complaint coming to this lab, because at FABE, the heart of nuclear physics is going to beat for the next 2 decades. And there was an illustrious article, a review article by Professor Henrik Satz, which completely omitted the contribution of nToF. The paper was referred to current trends in nuclear astrophysics and completely omitted the nToF contribution, which was something that somewhat hurt my feelings. So I wanted to show you here some selected papers concerning germanium isotopes, the cosmic ray, gamma ray, aluminum 26 emitter, gadolinium, and recent work by Carlos Guerrero about the process branching point here via time of flight measurement and activation. But now let's come to our recent research activities, and I'll start with the latest experimental station, the NEA station, beamline. So we have to characterize the neutron flux at the NEA station. This was initially done by simulations, as I told you, using FLUCA and MCMP, but it has to be verified with the irradiations using the multiple foil activation technique, and then subsequently by measuring the gamma ray yields with high purity germanium detectors. Of course, the most difficult part is the deconvolution of the experimental activation rates. Needs unfolding based on Bayesian analysis for the high energy region and via the SAND code, which is our task, up to 20 MeV. And this will provide the continuous feedback for new simulations, new improved simulations, I'd rather say. So this is basically the illustration of the activation method just for our younger colleagues, where the flux, the neutron fluence, sorry, is related to the cross-section with a rather complicated relationship, but basically it's an old technique. It's the oldest technique maybe for measuring cross-sections. One has to correct for the efficiency of the detector, the self-absorption factor, and basically for the times here, for the times between the end of the radiation, that's waiting time, the measuring time, etc. Actually, in this case, the radiation ended at CERN 20th of October. The measurements with the gamma ray detector ended a few days before my arrival in the States, and the analysis is in progress. So it's really fresh from the pot. This is the radiation setup we use with different targets. You have to realize, of course, that many different foils have to be applied because the flux, the neutron flux at CERN is a so-called white flux beam. So it has many energies. So it has to be very well characterized using several foils. We shall use 6 capsule reactions to characterize the low energy part, and 10 threshold reactions for the high energy part, up to maybe 100 MeV. We'll see how it goes. And these are the first spectra. You can see they are quite complicated. For example, for the high energy part, no, for all the for the GO foil, you can see the N gamma reaction characteristic line, but you can also see N4N reaction, which starts at 50, 60 MeV. And as I told you, one has to be very careful with simulations, because from what we see from the measurements is that the general trend shows that the count rate for the threshold reactions, namely NP, N2N, N4N, etc., seems to be higher compared to the expected ones. So the simulation results have to be tuned before the proper moderators are applied and NEA station be given to the general public for nuclear astrophysics measurements. Nevertheless, we believe that we will have the NEA station ready within 2022. And then let me come to the fission measurements, which I prefer. And first of all, why fission and what is its role in nucleosynthesis? If you check this quite popular diagram from Wikipedia, you will see that the elements are reported according to the most probable origin, merging neutron stars, Big Bang fusion, etc. But there are some which are denoted as human synthesis and no stable isotopes, and start immediately after plutonium, which is denoted as originating from merging neutron stars. Of course, this doesn't mean that these elements do not exist in the universe. It means that they are on Earth. Their presence on Earth cannot be attributed to a supernova or merging neutron stars because they have very small, very short half-lives. So here on Earth, they are produced by human interference. But in general, there are many existing open questions regarding these very heavy elements and their creation in the universe. And according to a few theoretical papers published relatively recently by Thomas Rauscher, Panov, Martinez Pinedo, etc., the neutron-induced fission in merging neutron stars, that is in neutron-rich environments, and core collapse supernovas may be more important than beta-delayed fission in the R process, which is the main, according to our scenarios, the main, I would say, the main responsible for the creation of these ultra-heavy elements. So our idea is that in neutron-rich environments, with like merging neutron stars or core collapse supernovas, following the R process leads us to very, very far away from the line of stability. We have quick neutron captures, which are broken at certain points with neutron-induced fission because of the neutron-rich environment. It leads us to, it feeds the whole table of elements, I would say, diagonally upwards. So this is the basic scenario by Thomas Rauscher and colleagues. So it will be interesting to study fission measurements, especially at very low energies, if possible. Neutron energies, I mean, even subthermal energies. So that was the first experiment we tried at Area 2. Because if you remember from our previous slide, plutonium is exactly at the interface, and it's mainly attributed to merging neutron stars. So we started with the famous plutonium-240, which is one of the most long-lived plutonium isotopes, and it's also built up in nuclear reactors. About, as a matter of fact, about 60 kilos are discharged annually on Earth per reactor. And it can be also considered as a nuclear fuel, as a matter of fact. In the high priority list of 2008, published by the International Atomic Energy Agency, high quality data needed in this energy, in this broad energy range that you see from 500 eV to 6 MeV. So we try to extend this to as much as possible to satisfy our scientific worries, I would say. That was, as I told you, the first experiment that was carried out in Area 2. And it was carried out by our group. And at low energy, you can see there was only one very good data set by Weston, measured at Oak Ridge in the past, in the 80s. All the other data sets are either erroneously compiled or they are very discrepant with one another. So there's a lot of room for improvement in the low energy region of a few hundred EVs. But if you go to the high energy, the situation, although it is improved, it is still not ideal. You can see with the black color, the data by Tolleson measured at Los Alamos in 2009. Still, the discrepancies, even at the plateau of the first chance fission, are larger than 10%. So it needs improvement. And why in Area 2? It was not because it was a new area, but because our group tried, we have to be honest with our failures, not only with successes. Our group tried to measure 240 plutonium in Area 1 with no success, and I'm going to show you why. The reason is that plutonium-40 is a highly radioactive target. We tend to believe that gas detectors are insensible to radiation damage, but this is not true. Look at this. Due to the low neutron flux, the sample had to remain inside the detector for several months in Area 1. You can see the distraction from the alphas emitted, because it's an alpha emitter essentially. All actinides, high mass actinides are alpha emitters. The distraction of the detector shown by the discoloration in the copper mass, sorry. And this is with a microscope. You can see how the micromass has been destroyed or altered. Even the holes here have been destroyed, as you can see in the right-hand corner. So we tested the performance of the detector at the beginning and at the end of the experiment, and we were losing counts. So this data could not be used for high quality measurements at all. So we decided to repeat the experiment in area 2, where due to the high neutron flux, the radioactive target would remain inside the detector for a very much shorter period. So we did that. I'm not going to bother you with all the details because the experiment is not so hard itself. But the analysis is quite complicated. It really deserves a PhD, as a matter of fact. It is done with the so-called relative process, where the cross-section is calculated relative to a standard cross-section that is well known. The formula is like a train here. You have to account for all the correction factors. Just to show you this with blue, I have marked all the minor, I would say, correction factors for self-absorption, neutron self-shielding, spontaneous fission, cluster decay. This is a basic parameter. What is, you have to know very well the flux in the area has to be very well characterized, but also you have very important correction factors marked in red. You have to reject fission signals because you introduce a threshold, of course, below which you consider that the signal is a noise. You may lose some signals. You have parasitic counts from impurities. This is a very important problem, which is many times ignored or looked down upon in nuclear physics. The target, the quality of the target, is sometimes the most important issue in performing a high quality experiment. And we have also counting losses due to pi 11 dead time, and this led to a publication even for the dead time correction models in time of flight measurements from our side. So what I wanted to say here that it's not trivial to derive the cross-section and know all the factors for the error. Anyway, the final result is that we managed to measure the cross-section for 9 orders of magnitude, from 9 millieV, that's below the thermal region, to up to 6 MeV. And that was the first experiment that was successfully carried out in area 2, as I told you, and illustrates the capabilities of the facility of this new experimental area. You can see the resonances, you can see the whole region up to the high resonances, resolved and unresolved resonant region, and the high energy part up to almost 6 to 10 MeV. So for the low energy region from 9 to 400 millieV, this is the only data set that exists. You can see many points. There were only the 2 previous measurements, highly discrepant, and do not cover this low energy area, which is important to describe the 1 over V velocity behavior of the neutron for the cross-section in this energy range. Now, this for the first time, we characterize this low energy resonance at 1.05 MeV. You can see that all the previous, all the evaluations used the poor resolution dataset by Leonard in the past, and they didn't manage to reproduce the experimental result, which we hope that the future actually is an ongoing process. The new evaluation will use this data because these are much better data for the description of plutonium. Okay, and for the resonance region, you can see that the Western dataset actually for a set which is limited in energy range was superior to ours, which was carried out at Oak Ridge, because at nToF the resolution was not in area 2 was not so great, as I told you in the beginning, due to the time of flight limitations. But all the other data sets were inferior, I would say. And you can see our the comparison with the other data sets ours are denoted in black. For example, in Miñeco, you can see heavy contamination by plutonium-239, which was attributed to 240, which is not true. Now we know that this is due to the poor quality of the target. So, Western and present data sets, we have a relatively poor response function due to the small distances I told you, very 2. And we have a Doppler shift. So, Western data really envious, but it has to be acknowledged. In some cases, we go to higher energies, we tend to come closer. As you can see, now we have reached the KV region. It's like a film. You can see spanning several orders of magnitude. There, above 6 KV, we are more or less the same due to that. You can see, and these are really data now. We have a double confirmation that the evaluators could use to calculate the convection. Yeah, and it goes higher up to 24 kV. Here, all the data. And now the high energy region, again, up to 6 MeV. You can see how our points follow the general trend within the low energy part. And after discussion with the Los Alamos people, they admitted that they're indeed 5% higher than the nominal values. So we believe we're in the right track. So then we tried, because it's beautiful, I mean, for a young guy to see when PhD candidates, when they finally measure the data, they're really happy and they feel confident. And then it's a good time to see whether their experimental data can be explained through a theoretical context. And this is, I think it was a beautiful example for younger guys because it covers several orders of magnitude. It has resonances, the cross-section has resonances, it has Hauser-Feshbach calculations. So see the whole picture, please. So for the EV-KV region, we have resonances, and we have to use the R matrix code for the analysis. And this is our experimental results and the code, the results from SAMI. We know the response function of the area very well. It was introduced in SAMI. We introduced the Doppler shift. And you can see the reproduction of the famous resonance at 1.05 EV. And then you can see with red is the theoretical approach, and with the black are points along with the statistical errors. And you can see here the resonances being beautifully reproduced with S-wave neutrons. It goes up. Yes. Almost all the resonances were reproduced beautifully with SAMI up to the rays, I would say. All these are fission resonances. And then for the MEV region, we used, of course, Hauser-Feshbach calculations, implementing TALIS and Empire, and we used for the level densities the generalized superfluid model introduced by Ignatiuk. And we had to modify the fission barriers, the phenomenological fission barriers which exist in Ripple 3 by no more than 10% in order to accomplish the theoretical calculations. And there you can see our final results with the Empire, where not only the fission, but the other experimental results for total cross-section, elastic, neutron, gamma, and then of course there are no experimental results. This is the weak point in the analysis. And fission results are reproduced. The low energy Empire is very poor, I would say, in the low energy part concerning the competition between gamma and fission. TALIS, on the other hand, TALIS 1.9 that we used was equally good in the production of the other channels. N gamma is better reproduced in Tallis as well as second transmission here, but the first transmission is not so well reproduced. Well, there are some minor differences between the codes, even if one uses the same, basically the same model for the level densities. And this was published last year. Thanos is currently, as I told you, at Los Alamos as a postdoc. And fresh from the pot, again, that was completed a month ago by another PhD student of our group, is the study of thorium-230. And there I'm just showing you this because we went, this was carried out in area 1, between 0.5 MeV, that was for fast neutrons, and we extended it up to 400 MeV. And I'm showing you this because it will be interesting to show maybe that our younger colleagues not to trust the evaluation libraries so much. Look at this. In the low energy, relatively low energy part, up to, I would say 10, maybe even less MeV. nToF is really good. It reproduces the experimental data in a beautiful fashion, but TENDU, which is, at least in our group, heavily used in JINA-4 simulations or in other cases, fails in a large way to reproduce the experimental data. And if one goes above 1020 MeV, then the disagreement up to 400 MeV is huge, almost half an order of magnitude. So evaluations and evaluated libraries need to be tuned to experimental data, and being an experimentalist, this gives me life. Of course, there are data have the best overall agreement with nToF and ZenBlue libraries. And when one tries to investigate also another limitation, the fission with using default values in Empire or Tallis, again fails miserably. One has to tune, has to do adjustments, has to tune the fission barrier widths, the level densities as well, increase the density in the high end part, do some kind of sculpture to modify the simulation as to reproduce in a rather satisfactory way the experimental data, and this is the result of the relative tuning. Unfortunately, we couldn't. This is beautiful. This is what really motivated me back in 2007 to propose this type of measurement. The existence of this high energy resonance, which is difficult to explain in fission with class 2 states. Unfortunately, we didn't manage to reproduce. It needs arithmetic calculations, but our resolution was not so high to allow us to deduce physics parameters from this measurement. But we had high quality data to 400 MeV, so we're satisfied. And this is to be submitted to the collaboration very soon, within the end of the year. So this is the end of my talk, I would say. Future perspectives. What are our plans? First, to study the americium-243 reaction. It is scheduled for the campaign 2022-2023. N gamma in americium-243 has already been completed. It will be published soon. That was for the S process, and this is for neutron-induced fission. So we need to introduce new experimental capabilities at nToF. There are some ideas, some expensive ideas, to change our barium fluoride sphere for the calorimeter and use high purity germanium sphere. This would allow us to study NN prime reactions as well, which for the time being we cannot do because barium fluorides do not have a good energy resolution to study such reactions, and partial, I mean NN1, NN2, NN3, we cannot do that right now with barium fluoride we have. There is an open question about the angular distribution of the fission fragments. I noticed here at FRIB, there is a PPAC setup to study, which really interests me, to study the angular distribution of fission fragments. I have in mind some ideas to study with double-sided silicon detectors and position-sensitive microdetectors. We'll see. We'll see. And we need to efficiently address the problem of the gamma flash. Due to the spallation process, we have a huge load of garbage particles that hit our detectors and blind them for a considerable amount of time. And we need to be extremely cautious. And these limits are high energy data limits. But the most important one is that we need to transfer to another planet, most probably, where the day will last longer and the funding for nuclear physics will be unlimited, with my dream. And without needing to write and submit any type of written proposals, because this is time consuming and time waste from science. Thank you very much for your attention.
Okay, thank you very much, Mike. Let me start with some questions here from the local audience. Belly, please go ahead.
Sorry, Belly.
Maybe, can you just repeat the question, maybe?
I cannot hear you even myself.
Ah, okay.
How do you tell this? Ah, okay.
So you mentioned here the problem with the gamma flash on the neutron flash.
Yes.
You also mentioned that you also have a new experimental station, the NTUA station, that we got to
Yes.
So
Yeah.
how can you correct that?
I will not.
But then the
No. This is the peculiarity of the NEA station. At the NEA station, we are not going to introduce any detectors. So the idea is to study the flux characteristics of specific points near the spallation target. So we'll know the flux in a very accurate way, and then using the multiple fold activation technique, and then without putting any detectors, we'll put the samples. The samples will be then removed after the irradiation. They will be measured offline in a lab. I mean, with the offline gamma ray detectors. I mean,
and then the for the
yes, this will be done a priori with the multiple fold activation technique. I mean, this is what we're doing right now to characterize the flux. Of course, the flux is not symmetrical. You know, there's no spherical symmetry in there. I mean, you have to put to dedicate certain points, and in these points, where we are going to mount our samples in the future for nuclear astrophysics measurements, we put all the stack of how should I say activation foils for which we know the cross section, and then we'll convolute the cross section, find the flux, and then we'll say you can measure here. This will be your Maxwellian average cross section. If you measure here, you have this type of spectrum. If you measure there, the other one.
We have a question from Zoom. Alexander, please go ahead and unmute yourself and ask your question.
Hello, everybody. You hear me?
Yeah, we can hear you.
Okay, so my name is Alexander Buin from Ohio University. I'm curious, you mentioned that you did a lot of N-gamma measurements in the beginning of your talk, and you showed a list of publications, and specifically you showed N-gamma of germanium isotopes. So could you elaborate a little bit more on what kind of data did you get and how it compares to model calculations, probably? Because interest is, as you know, we studied germanium isotopes in Artemis group as well with beta Oslo method. It would be interesting to see what kind of experimental data you got from your experiment to be able to maybe make some comparison.
Yes. First of all, maybe I was misunderstood. these measurements were not carried out. The list of publications I presented was not carried out by our group. It was carried out by members of the collaboration. Actually, this is as a matter of fact, this is Claudia Lederer's group, and these are her students and postdocs, Dietz, Golik, and herself. She wrote the paper. So, but I can how to say, bring you in contact with her if you want to specific details. The way our collaboration works is that there's a team responsible for each experiment, and it has the leading role, and the others are collaborating with shifts, with support and stuff like that. So we were only for this, especially I didn't put any publication from our group in this short list because you know, I wanted to show the other groups. The Spanish people, the Claudia's group, yeah, maybe basically these are, and the Italians also who measured gadolinium. So I didn't include it I didn't include in this list our work. Our work was presented in the other parts of my presentation.
Okay, thank you.
I don't see any other raised hands on Zoom. Are there any questions from the local audience? I had maybe a curious one. So, of course, here at EFRI, we're trying to push to more and more radioactive isotopes. So I'm curious, how short-lived can a sample be and you're still able to measure?
Oh, that's a very good question, as a matter of fact. That's a very good question because, as you know, we obtain our targets from certain places. JINA-CEE in Belgium, JINA, that is, IRMM, some people know it like this, and also the Russians at Obninsk. And in both cases, can I make a comment here? I mean, these are highly bureaucratic establishments, and by the time the target leaves that establishment and arrives at CERN with the proper container checked by the how to say, the RP, Radiation Protection Department. I mean, the answer to your question is not short enough. Not short enough. It has to be long enough to survive. The target should survive the bureaucracy, not the measurement itself, the bureaucracy, I would say.
Wow.
Okay.
There's one more question on the line, two questions. George, go ahead.
Hi, Mike. So I saw all these measurements with a lot of interest. And my question is, I saw you're measuring mainly gammas and fission products. Is there any thought of measuring charged particles from neutron-induced reactions?
Yes, there is. There is. By the way, Professor Petikakis was working with me at nToF, and he was the first student I collaborated with, and my favorite student in the past.
Oh.
And yes, and he knows very well that the initial, how should I say, purpose of nToF at CERN, which justified its existence, was the measurement of fission fragments and the fission of gamma rays for nuclear astrophysics. So we're really trying lately to introduce charged particle reaction measurements like NP and N-alpha, which can be very beautifully carried out with gas detectors in area 2, I would say. And there's a whole collaboration right now led by the Catania people in Italy. Maybe, George, you remember Agatino Musumara?
Yep.
Has currently a leading role in trying to set up detectors, silicon detectors, which would tolerate the gamma flash without being blinded and measure charged particle reactions. And if this succeeds, because he came to Democritus to measure with us maybe 2 months ago, if this succeeds, of course, we would like to participate as well. And you're kindly invited as well.
Thanks, Mike.
Stefania, go ahead with your question.
So adding to Artemis's question about the targets, how happy are you with the impurities, the way that they're made, how clean they are? And if we're talking about long-lived as 243 americium, have you thought about getting targets from the US or?
Yes. First of all, let me ask the first part of your question. How honest should I be? Okay, I'll try to be as honest. I'm not satisfied at all. I'm not satisfied at all. Because many measurements have been killed because of impurities, but these impurities are killing the most interesting part for nuclear astrophysics, the low energy part, where we have resonances and stuff, because the cross-section they have for fission is huge, orders and orders of magnitude higher than the corresponding target under measurement, and they create a lot of problems. This is something universal, as a matter of fact. I showed you measurements from the States which had the same problem in, previous years. So I'm not really satisfied with our how should I say, providers right now. And I sincerely hope that nobody from Belgium or from Obninsk hears me, because we still need them. But for the americium and gamma measurement, we used the States, as a matter of fact. We used a company from the States to buy the target, the first set of targets. For the second, because we need a thicker target for the fission measurement, thinner target for the fission measurement. The negotiations are still ongoing, but it's a company. It's not an academic establishment, I would say.
Okay.
But I would be highly interested, of course, I would be highly interested to have, a collaboration which would lead us to better targets and would allow better measurements in the near future. There's no doubt about it. And if such an option exists, and this is the main reason, any type of possible collaboration with our friends and colleagues in the States was my main motivation for coming here.
Well, Notre Dame is actually, we're using a new technique and we're making ultra thin to some thicker targets. And I'm going to be working with americium starting like New Year's. So
let's be in touch then.
Yeah.
Let's be in touch, because the measurement is scheduled for the 2023, actually, end of 2022. So there's plenty of time to.
Actually, with the method that we're using, thinner targets are a lot easier made than the thicker targets. And we are making impurities free, no defects in the surface. The targets themselves look beautiful. So,
wow.
Yeah.
Wow. Okay. I'm not in the target business. Concerning the text, I can say, great, or start complaining. That's all I do. But I don't underestimate the importance and the quality of the measurement. This is highly, highly important. Although it's as I told you, it's somewhat neglected when we're doing theoretical analysis or matrix calculations or house of Pascal calculations. But the quality of the target is the real essence of the experimental process.
it is very essential, and physicists look down on the people that make targets. I'm going to tell you that.
No, I don't. No, I don't, because of as I told you, this experiment in area 1 was killed with plutonium-240, and we spent 2 years measuring it. And analyzing it. Just to give you an example, not for the quality, because of the radiation damage of the detector. So this is a solid-state physics process, if you like, but it killed the nuclear physics experiment, and it had to be repeated under different conditions. Therefore, physics is interdisciplinary, not. Yeah.
Thank you.
Last chance for question on Zoom or locally. I don't see anyone, so let's thank our speaker again.